Okay, question 1. A bottle of the solution is missing its label, so it is either the lead, barium, or iron to nitrate. So your task is you need to identify what the solution is, the bottle solution is, using only, can you read that? Only hydrochloric acid, sodium hydroxide, sulfuric acid. This is why I've been saying, no, you can't use a flame test. You're only allowed to use those three. If you write something out of this, you will get a mark deducted even though your point is right. Okay, just be aware of this type of question too. And you also need to write a sequence of the steps. Means what? You need to write a methods to find it out. That could be followed to confirm the identity of the solution in the bottle. And you also need to highlight these guys too. Observe the result and ion equation. These are counted in your marks as well too. So even though there's a 4-marker question, you need to write quite a lot to get full mark 4 out of 4. It's not an easy question to get the 4 if you're not too sure about how the steps. So this is what I recommend you to do. Make sure you use the given space on the top over here. Okay, you don't put the flowchart in the given the lines here. As soon as you put these here, this is going to be marked. Okay, and you can get a mark deducted by doing so. Don't use that. The question didn't ask you to draw the flow chart, but use the flow chart. Use the space to draw the flow chart to help your writing your answer. So what you can do, you collect a sample in a test tube, just one test tube. Okay, and what you do here is you gotta choose one thing here. So you can choose either go for like sodium hydroxide, hydrochloric acid, and sulfuric acid. So, but I think it really depends. You can start off with adding some hydrochloric acid if you would like to. Or you can choose to the sodium hydroxide as well too, because we know that hydroxide forms the precipitate with the most of the cations. So I'll probably leave that for now, so to get the hint over here. So what we expect is the hydrochloric acid, okay, or chloride ions would have formed the precipitate with the lead only. So you can just go like here, forming a precipitate. Okay, that means what color? What do you mean? What color of the precipitate?
White.
White. And this is the lead aqueous plus chloride aqueous forming that lead chloride solid. Okay, if it's forming, then it's kind of identifying that this must be the lead nitrate straight away if it's formed the precipitate, because we know the chloride would not form the precipitate with the barium nor the iron 2. Is that clear? Okay. Catch. Okay, then if not, no precipitate, what you can do in the next step? Tell me, what would you do in the next step?
Add sodium hydroxide.
Sodium hydroxide, okay. Okay, let's add the sodium hydroxide, add that. And what do you expect? If you're forming the precipitate, yes. You can just write the yes for the precipitate, yes.
Iron 2 plus.
Iron 2 plus aqueous, forming the precipitate with the hydroxide ion 2. That what? Iron hydroxide, solid. Color. What's the signature color of the iron 2 plus?
Red.
Green?
Blue.
Blue? Green. It's a green. So the green color, green precipitate would be formed. What about the barium? Barium would not form the precipitate with the hydroxide, does it? No? Barium doesn't form. So, if no, move on to the next. What do? You add sulfuric acid. And if that's a yes, it must be then, show the ion equation that barium 2 plus aqueous plus SO4 forming the barium sulfate. What color, John?
Barium sulfate.
Green. Green? Nothing.
White.
No, okay. I mean white.
You said green and I was like, wait, what? Green? There's more of a green.
Do you trust Jongmin?
I don't
Do you trust the guy
That's
send me
my
a
feeling.
the report that what is alcohol to the one line? Okay, I don't trust him anymore. You tricked me.
No, I sent it to you in advance.
Yeah, but I was expecting something more than what is alcohol. But okay, just working on that too. I'm kidding.
I could get it finished by next Friday.
That's, of course you have to. All right.
We
the-
did the prep next week.
Good. Flow chart is done. Now, what you need to write here, okay, when you're writing the outline, because that's writing the methods, you can't just say, hey, I add hydrochloric acid. I did something. You must write that in the specific concentration as well as the volume you're going to use. So what you do is you must say that 0.1 molar of the, a few drops of the hydrochloric acid to the test tubes. In each of the steps over here, you must phrase that, you must say that you're collecting the new sample. You can't reuse the test tube over again, again, and again. So that's what you need to put in your each of the steps. Do you get it? Okay, so your step could go like this. Collect the sample in a test tube, add 0.1 molar, add a few drops of the 0.1 molar hydrochloric acid, and look at observation that if it forms a precipitate, white precipitate, it must be the lead chloride with this net ion equation. If it doesn't, okay, collect the, so you must say collect another sample in there, add 0.1 molar of the few drops of the 0.1 molar sodium hydroxide in it. Look for the precipitate. If there's a formation of the green precipitate, that must be there. That must be indicating the presence of the ion in it. Okay, you repeat the same step. Collect another sample. Add a few drops of the 0.1 molar of the sulfuric acid. Okay, the reason why I'm picking up the higher concentration is there are some cations that only form the precipitate with the higher concentrated value. For example, calcium with the hydroxide. Okay, so you have to choose the correct, you can't just use a dilute or something. You must say like very specific values, that includes concentration and amount of you're going to use in your method.
Can you just use NaOH to find molar?
Okay, what do you expect by adding the NaOH?
Well, NaOH would just form white precipitate with Pb,
Mm.
and no precipitate with Ba,
Mm-hmm.
and then green precipitate with Fe.
You can. You can. So you can write a method about if that forms a white precipitate, there must be the lead, and if it forms a green precipitate, it may be iron too. But I think that's what Dongyu asked me to get into. Yes, you can, but I just recommend you to use all the given solutions if you have the options to use them all. You still can get a mark, but depends on who's marking your paper, depends on what sample as they have. They sometimes get questioned like, what about the sulfuric acid? What about the other, like hydrochloric acid too? Okay, so there could be a multiple answer for this. You don't have to start from the hydrochloric acid. You can start from the sulfuric acid if you want to. That's fine. Okay, but what we're going to look in your answer is we're going to look for the correct net ion equations with the expected the result, which is the color of the precipitate, with the which solution you put it in. Okay, good. Question 2.
For the ionic equations,
Yeah.
you have to make 9.
Do I have to make what, sorry?
9 equations.
9? No. Why should you? You just need to write the ionic equations for the when there's a precipitate is formed. That's it.
But then you also have to write like this plus this doesn't form anything.
Then it doesn't get the net ionic equations. Think again.
So
Think again.
you can just ignore it.
There's no equation. There's no reaction. There's no ionic equation then. Get it? Okay. Next one. Question 2. Describe how different observation from the flame test would allow a student to distinguish between the solution containing barium ions and copper ions. Jeremy, what's the color of the barium ions flame test? The flame test. Yellowish green, yellowish or yellow green. Calcium,
Just green.
brick, calcium,
Oh,
copper. Oh, sorry, copper. My bad. Yeah, my bad. Yeah, copper is just a green. kind of bright green we're expecting. We kind of like discuss about like the difference between the colors of the red colors, crimson, you know, scarlet, red. Apparently, what I asked to that, I needed to ask to my wife about like the lipstick colors, because they actually had a.
Oh, they all look the same.
Exactly.
It's
I think that's a
so
problem.
stupid.
That's a problem with the boys.
They go and they're like, and it's the same
It
color.
is,
It's the
it
same
is.
color.
Okay, I got the ideas from my wife. Like, how would you distinguish between scarlet and crimson? She would say, "Oh, that's a B something." She was like, especially giving the color code or something.
What the?
Yeah. Anyways, scarlet is like something more like pinkish red, more the pink kind of red, like some sort of phenolphthalein colors, some sort of that. Crimson is more like a kind of dark red. And you can just think, yeah, it will be like, they are freaking red. I know, yes.
Like blood red?
Blood red is more to the brick red of the calcium.
Isn't blood dark red?
So, brick red, as in like, you can think about like when the blood stain, the color of the blood stain, when it goes like solidified, yes, that's kind of brick red color. Okay, or you might see like the brick red house, the red block houses, those colors. That's the color of the flame of the calcium. Anyways, that's what I got from my wife, and hope that's right. I mean, this is right. I checked in the Google, so yeah. All right, 3. You are given an unknown solution that is suspected to be aqueous calcium iodide. Describe how your test you could perform to confirm the solution identity. Assuming the your suspicions are correct, then state the expected observation. So what you have to do, the reason why it's a full marker is you need to set up the experiment for one for the calcium cation, another for the iodide. Okay, so there are various methods that we can test for the calcium. First of all, yes, you can do the flame test, but I might be avoiding using the flame test, especially for the calcium iodide, because I don't want my room to be full of the iodine gas. Does it make sense? So, yes, you can, but it will have some safety issues. So, instead of using the flame test, so you show the brick red, by the way, color of the calcium flame test. Instead of doing the flame test, I would probably go for the precipitation test. Now, how do we test for the calcium? What solution should we use to get the precipitation of the calcium? Sulfate. So, what do you expect? Adding the sulfuric acid again, or something sulfate. What do you expect? Why precipitate with the calcium? Yeah. So we're expecting the calcium, aqueous, with the sulfate 2 minus aqueous from the calcium sulfate solid with the white precipitate. Anything else? Can we like confirm that there's a presence of the calcium, because it could be a barium, you know? Anything else? Can we confirm that? The OH test. Okay. So what OH should we use the concentrated OH? Diluted OH? The calcium? Are you sure?
No,
Isn't it always diluted?
concentrated.
Concentrated. Read that again. So yeah, you have the concentration must be greater than 0.05. So you must either use sodium hydroxide, which has a greater concentration, or greater than 0.5 molar.
Right, so can't you just use like dilute OH and test it again with sodium and atmosphere?
Dilute with OH and
Yeah, and use it.
and the sulfate.
Yeah, not sulfate.
Which one then?
Fluoride.
Fluoride.
Yeah, fluoride.
But that'll be same for the magnesium, isn't it?
Magnesium won't produce any like precipitate
With
so 2 minus.
no. But yeah, so I just need to do 2, not 3.
How about PB2 plus?
PB2 plus,
Yeah.
the lead,
Yeah, lead also produces
white precipitate, and that too. So in that case, you need to adjust the using the concentrate. This is the key. Okay, so first you need to use a dilute sodium hydroxide. Second, you use concentrated sodium hydroxide. Okay, yes, you may do like a flame test, but as I said, I've tried to avoid using the flame test because it might be a lead. It might be a lead that you have given the solution here. So you can't just trust your suspicion, like, oh yeah, I feel like this is the calcium, so I'm gonna do the flame test. But if that's a lead, you're basically exposing all the lead particle into the room. You get the heavy metal toxicity, and we don't want that to happen, basically. Okay, so we try not to do that in the real practice. So as we know, the calcium only forms the precipitate with the higher concentration. So we check whether if the solution does not form the precipitate with the diluted sodium hydroxide, with the concentrated hydroxide, that's kind of test giving you the idea that this must be the calcium too. Okay, once you get it up to here, once you get your suspicion to get it correct, then you may perform a flame test. You may, with a little bit amount. All right, what about iodide? John, how are we going to test for the iodide then?
Iodine.
What would be the way we can test the presence of the iodide? Again, we can use the precipitation reaction using what? Silver ion. So for example, silver nitrate. What we expect? Silver with the iodine or iodide forming what? Yellow. What yellow? Silver iodide, which is the pale yellow precipitate form too. Okay, that's how you can test for both the calcium and iodide. Yes?
So are you just putting in silver into the calcium iodide solution? Are you putting in like silver?
Oh, you got to, yeah, you're given like describe the test, yeah. So you you're performing two tests, two separate tests.
With same solutions, right?
Yeah, because you're given the one solution there again.
So when do you use dilute sodium hydroxide?
Does calcium form the precipitate with the dilute sodium hydroxide?
Does it?
Does it? Calcium. Does no, Jomi, you're on the right page. Does calcium form the white precipitate with the dilute sodium hydroxide?
Oh,
Thank
it says
you.
right there. Okay.
Thank you. Yes, it's been there.
Okay, when do you use dilute?
When do we use dilute? Means others except the calcium would form the precipitate, even with the diluted.
But then we always use concentrated HCl.
Because because the calcium is sparingly soluble in the hydroxide.
Oh no, wait, we do dilute HCl.
Yes.
So you just put in like dilute NaOH first, and then the concentrated NaOH second, like just excluding the SO42 minus.
You can, but I just want to confirm whether that's a calcium too. So that'll be safe because it might be wrong, you know. Or you can use your flow chart if you like to, like to test for the calcium ions too. You can either use sodium hydroxide with the calcium. So you can add some like a fluoride in it, and it forms the precipitate as well too. So there are various methods you can do. But one thing we can't do for the calcium is because it's a group metal, we can't expect to have the complexation or complex ions. Remember that complex ions can be only formed by the transition metals. Like for example, copper, iron 2, iron 3, silver, lead, what else? Like some cobalt as well too. Question 4, how'd you go? You alright, John?
Yeah.
4,
Precipitate rule
are you sure?
Yes. You guys have rule form? Isn't it just the... Because you do the moles.
All right, question 4, let's start here. So we have a mixture is formed from 0.14 mole of the sodium chloride, 0.065 moles of the lead nitrate in 4 liter water. So what we have now is lead chloride solid will be dissolved in the form of the lead aqueous plus lead chloride 2 minus over here. Let's find the concentration of the given lead. How to find this? The C equals to N over V. That's N is given as for the lead. Lead is same as the N of the PbNO3. It's good to show this in your practice. Okay, so from here, N of that divided by the volume. That's given as what? You have 0.065 divided by the 4 liter.
0.01625.
0.0.
1625.
Yep. Mole per liter is the first one. Same for same process for the chloride. Chloride given. Dongyeol, what would be the amount of the chloride given? What would be the concentration of the chloride that's given? Hmm? So that's the same as N over V. So using that sodium chloride here again. Okay, make sure you show that, because you'll be get a question like, hey, where'd you get the chloride number moles? It's actually given from the sodium chloride. That again.
That's including the reaction ratio, right?
Yeah, because this is why I just used that same ratio here. It's a 1-to-1 reaction. 0.14 divided by 4, which is what?
0.035.
0. Yep. Question. Do we need to count for any of the limiting reagents for this question?
So we have to find excess.
Do we have to find the excess? Do we have to deal with any of the limiting reagents for this type of question?
No.
Why?
You don't.
No, you don't.
You just put into the KSP thing.
Exactly. This is why I write that given. You're given this. You're only given this. Then, time to find the QSP, the quotient. QSP can be found by what? Lead concentration times that chloride concentration squared, which is 0.10625 times that 0.035 squared. Don't ever try to find the limiting reagent or something. This is not a question for that. Then you'd get 0. That times 0.01625. Yes, indeed, but we still get it in the measure 8. Okay, 1.99 times 10 to the power of minus 5. That's a QSP value. Now, what's the KSP?
1.7 times 10 to the minus 5.
1.7, or just 1.7 only? 70 times 10 to the power minus 5. Which is bigger? That's a KSP, that's a QSP. QSP is bigger. Therefore, yes. Easy. Module 5 question again.
Would that be like a 2 marker?
Yeah. 2.
It's a 4 marker.
Oh, what?
I don't know why.
Hey, 4 marker.
Maybe it's total question for is a 4. Maybe.
Oh, it would just be.
Maybe. Well, even if that's a 4, that's good. Good news. You got 4 out of 4 now. All right. Any questions about like the QSP? There's something we've done last week. No? All right, move on to chapter 2, page. So page number. I'm going to skip to page 59. Let's move on to page 60. So, the last week what we learned is basically a very straightforward qualitative analysis. Again, qualitative and quantitative. Jeremy, how would you differentiate the qualitative and quantitative analysis?
Quantitative is comparing
Amounts, yep. So exact quantity, yep.
Yeah. Qualitative is like color change, something like. Oh no, sorry. That's just more like
Mm.
just the other stuff. Observation.
What other stuff?
Yeah, like
Observations of what?
color of your results.
Of course, we are looking for results, yeah.
Smell.
Smell.
Sight.
Qualitative is simply, qualitative is simply testing for the presence of that cations or anions. That's it. We just want to know whether we have the calcium, whether we have the iodide, just like what we've done in here. That's called a qualitative analysis. We don't care about how much we have. We only concern about whether we have that or not. Is that clear? This is why we learned about flame test, precipitation test, and the complexation. Guys, sometimes you get questions like, hey, just analyze the qualitatively, quantitatively. Means that you need to identify with the qualitative analysis and then using these type of the quantitative analysis. The first quantitative analysis is known as the gravimetric analysis. That's basically, once you get the precipitate, what you do, once you get the precipitate, you filter it out, you dry it, and you weigh it. That means you should be able to grab how much of the anions, cations presented in that concentrate, in that solutions. The methods given here is to prepare your sample solutions. This includes dissolve a solid sample if required. Add the precipitation solution in sufficient excess amount. Highlight that you must use the excess, so that make sure all the ions in the solution get precipitated. To cause complete precipitation of the ion being analyzed, collect the precipitate by filtration and wash it carefully to ensure that no soluble components are trapped in it. And number 4, dry the precipitate carefully to ensure that the mass obtained is not higher than it should be. The precipitate is usually heated, cooled, and weighed repeatedly until its mass is in constant. This ensures that all water has been removed. So the way we can remove dehydrated water is we can use the oven. You can sometimes use electrical heater, or you just leave that for like overnight or day, okay, up to like 5 days sometimes, to make sure we evaporate all the water remaining here. This is very simple and straightforward and easy process. So what we can get, so page 61. This is one example of the gravimetric analysis we have. So 1, the silver chloride precipitate collected from 7.802 gram sample of the peanut butter has a mass of the 0.112 gram. What is the percentage of sodium chloride molar mass? Okay, this is a molar mass of silver chloride, guys. Sorry about the typo. There's a molar mass of the silver chloride, not the sodium chloride. In the peanut butter, I'm assuming that all chloride ions are present as a solid sodium chloride over here. So what do we do? What we do is we start from the amount of the mass. So you put the silver chloride, you make the silver chloride by adding some silver. So you're given that mass of the silver chloride precipitate we have is given as 0.112 gram. Okay, from here we can find the N of the silver chloride by what? M equals to M over molar mass. That's 0.112 divided by given molar mass value, 143.32. Okay, so then you to get 0.007675 mole, or simply 7.675 times 10 to minus 4, the same thing. What we know from here is the N of the chloride ion must be same as N of the silver chloride we have, which is same as 7.675 times 10 to the power minus 4 mole. And then go up to here, that's same as what? Same as the N of the sodium chloride in the peanut butter. Therefore, mass of the sodium chloride in the peanut butter can be found by N times the molar mass. That is 7.675 times 10 to the power minus 4. That times molar mass of sodium chloride. The sodium we have is a 22.99 plus 35.45 for the chloride. So use the saved up the value. That times that 22.99 plus 35.45. That you should get 0.04485 grams for the mass of sodium chloride in that given peanut butter. The question asks you to find the percentage of sodium chloride. It's found by what? Mass of the sodium chloride divided by mass of the peanut butter. That times 100%. So that is 0.04485 divided by peanut butter given as 7.802. Okay. So that's that divided by 802 times 100%. You get 0.57. No, sig figs. What are the sig figs that we have to fix? We're given 4, 3, and 5 sig figs. So as we divide the use the 3 sig fig value, you must fix then the 3 sig fig, which will be 5.75%. Is the amount of the sodium chloride in the given peanut butter. Okay, this is simply known as what? Module 2, like year 11 module 2 questions that we've been practicing quite a lot too. But you have to you should be able to picture that what is going on in the experiment. Therefore, you can solve the question here.
How is silver chloride and sodium chloride linked? Where does sodium chloride come from?
Your task is you want to know.
So the silver chloride
No, you basically had a peanut butter.
Yeah.
You want to know how much is sodium chloride in there.
Sodium chloride.
You want to know, how much sodium chloride in that peanut butter.
From the given silver
From the
chloride.
given, yes, means that you can induce the precipitate by adding some silver ions in it. As we know, the silver form the precipitate. Excess silver ions in that case. And we only take the precipitate out and dry and weigh that. Therefore we got the mass of silver chloride to be 0.112 given.
Oh, and then the chloride ion.
Yes, and we know the chloride ion has the same number of mole. Make sense? Okay, what about the next one? Question 62, question to page 62. Could you try this and the next try yourself question 2 now, please?
It works so well when you suck it.
Indeed.
Shouldn't it be half? Oh wait. Oh. Why did times half?
Okay, you should get 2.70%.
Can you see the third one? The first one.
Yeah, what about it?
I didn't get it though.
If I have one mole of that, how many moles of silver?
2.
There we go.
Oh, for AgNO3,
Yeah,
then you only have 1 mole of Ag.
I know.
But how's it equal to 2 moles?
No, I'm not counting AgNO3 yet. I'm counting for how many silvers in the precipitate of the silver chromate.
Oh, you said moles of AgNO3 equal to...
Yeah. Do you understand what is going on in the question? Okay, can you try to understand what is going on here? You're given a sample of water. What's the aim? What is the aim? What's the aim of the experiment or this investigation?
It's kind of like that
silver
titration.
chromate.
No, not yet. We're not even there yet.
To produce silver chromate, which is just the precipitate.
Why do we forming the silver chromate precipitate? For what reason? What's the aim of the investigation again?
To calculate the percentage mass of silver in the water sample.
Silver.
That's the aim.
Oh, why would I count silver nitrates? Okay, my bad, guys. Okay, I shouldn't do that. I only count silver. Don't worry about this. Silver nitrate. If that confuses you. I have to read the question again too. Okay, so that is the silver that we have. So let's try it again. Times 2 and times 107.9. Okay, it's even less. 0.586. So 0.8586 times that. Then you get 1.72%. Gravimetric analysis. Why are we doing this? We want to know how much of the silver we have, or silver ions, silver metals we have in the water, so that what we know about the chromate is it forms a precipitate with the silver. So we put some silver chromate ions in it, or solution in it, inducing that all of that makes to the precipitate, and then from that we can get it over here. I kind of confused because I thought we need to find the silver nitrate, or whole things. But you may get a question like, hey, what about the concentration of silver nitrate too? And don't get confused, because if you have a silver nitrate in the water, where is the silver ions coming from?
Just silver nitrate.
Yeah, so if you have a silver nitrate present in the water, where is the silver ions coming from? The silver nitrate, basically. So what we know is, if you have a certain amount of silver concentration, that must be same as concentration of silver nitrate too. It's 1-to-1. The reaction ratio. Okay, but this question is not asking the silver nitrate on the silver, so it's more easier. But what about this one? Finished this one yet? Not okay, almost. An experiment was carried out to determine the sulfate contents of fertilizer. 2.104 grams of sample of fertilizer was crushed, and excess barium chloride was added until the barium sulfate precipitate stopped forming. The precipitate was filtered and found to have a mass of the 2.553 grams. Calculate the sulfate contents of the fertilizer. So what we do, we need to find it basically the same things. The mass of the precipitate we have. So for this we have a barium. As we add the barium sulfate precipitate, the barium sulfate is known as 2.553 grams is the mass of the barium sulfate. Again, we can find an N of the barium sulfate by M over molar mass that is 2.553 divided by molar mass of barium is 137.3 plus the sulfur 32.07 plus the 4 oxygen. Then you must get, okay, and 2.553 divided by that, you get 0.01094 mole of the barium sulfate is presented here. Okay, so what are we interested in? We want to find that, calculate the sulfate contents, how much sulfate is in there too. So, or in terms of percentage, we can find that. So that is what? Can we say this is the same as the N of the SO4, 2 minus sulfate contents 2. Therefore, M of the sulfate, 2 minus, can be found by N times the molar mass, which is 0.01094 times the molar mass of this, so 32.07 plus 4 times 16.
1.051.
Okay, let's check that again. 1 point, you're right, 1.05098. I left that into some exact value over here. So let's find that in the content percentage value of the SO4, 2 minus. So that would be 1.005098 divided by the volume 2.104. That times 100%. So that divided by 2.104 and times 100, you get 49.95, approximately 50.0% is given.
But don't you have to keep it in 4 decimal place?
Why 4?
4 sigma.
4 decimal point. 4 sig figs or 4 decimal?
Sig fig.
Yep, I'll leave that to 4.
So wouldn't 49.95 be?
Is it 49? Oh yeah, you have 49.951. So yeah, I can leave that to the 4 sig fig values like this. Good. Easy. Calculation wise, like there's nothing you have to be afraid of. You know, been doing this, finding stoichiometric calculation quite a lot.
This is.
Oh, it's gonna be more fun. All right, let's have a 5 minutes break and then come back for some precipitation tests. All right, page 65. So we learned about some titration techniques from module 5 and 6, or from like year 11 too. Titration can also be used to figure out how much precipitate we can have here. So in here, there are some names given, but you don't need to memorize those names because that's not really part of the syllabus. But what you need to remember here is you need to know the features of each of methods. You need to know the possible limitations of them too. This could be related to some of the depth study questions or working scientifically the questions as well. You also need to know like how to calculate exact precipitation. So precipitation means, again, we're using some cation, anion. So assume that you're given something like some unknown solution of the cations or anions. We're inducing some precipitations and then figure out how much quantity. So titration technique is also known to be quantitative. So we always use titration to get exact number of moles or the concentration, even the grams from it. So the first method is known as the moles method. Okay, for the moles method, it's best to use the diagram given over here, the page 66. So what we do is we're using the silver solution, in the burette. So silver solution means like something in the burette means that we know exact concentration. So we know it's a known concentration. The silver solution used. The solution as in like it could be a silver nitrate, something that doesn't form the precipitate yet. And in your analyte here, we are supposed to analyzing the quantity of the chloride, iodide, and all the bromide. So the aim of this method is we want to get the quantitatively analyze the iodide, chloride, or one more, I forgot the one, and the bromide, not the iodide, chloride, bromide, or the cyanide. This is the aim of the moles method. Okay, we can't use for bromide and something else. So the way we use that is we're using a chromate as our indicator. So you have to know the difference between the acid and base in the titration. So for the acid and base, do you remember that we put the indicator, we put the we open the burette, and we see the color change until the end point. For this point here, we're using the chromate CR2, CrO42 minus aqueous is your indicator. So what happened here is this. We open the tab or the silver, put it into the unknown concentration of silver. This is an unknown concentration of the unknown concentration chloride ion there. So once you put in the silver into there, what we expect there is, first of all, the silver aqueous would form the precipitate with the given chloride, for example, from one over here, forming the silver chloride would be formed. As we can see that the precipitate is starting forming in here. Okay, we just leave that until it color change to the red. Now, once you get the red color, that's due to that all the chloride means that all the chloride gets used, and then chromate 2 minus started to form the precipitate with the silver ion. Okay, so very simple procedure. This is going to be a direct titration. You just pour some silver into the unknown concentration chloride with the chromate as an indicator. Does it make sense to all? There's something you can just refer to the acid and base titration again. So as soon as you put in the silver into there, silver would form in the precipitate with the chloride ion. White precipitate will be formed. Once all that chloride is used up, okay, then it started forming the precipitate with the chromate, forming that change the color from yellow to the red. And once you get the red color, you stop the titration, get the volume of it. You all right, John?
When you want to put like excess amount?
No, this is not for the excess amount yet. For the excess amount, when we're going to get the excess amount, that's known as the gravimetric analysis. I'm using titration, so we don't need to put the excess or extra amount of the silver into it.
Or just until endpoint reach?
Just for the endpoint reach, just like a acid and base titration.
Oh, okay.
So is this just basic titration?
No, this is one method known as Mohs method, using to figure out the concentration of that. There's no basic or something, some standard methods, because it depends on the situation, depends on what you have. You can use various things.
How does it change color? How does it change color?
How to change color? Okay, okay. First of all, silver and chloride has a high. I call it high affinity. Affinity means like they love to react each other first. I mean, chloride has a higher priority than the chromate. So silver also formed the precipitate with the chromate ion, forming that silver chromate. That's a red color. There's a red precipitate color here. But if we're thinking about the priority, because silver has high affinity, which means it loves to react with the chloride in the prior to that chromate here, this will be reacted first and then followed by this one. Okay, so there is some priority during the reactions as well too. Silver is prioritizing chloride, bromide, or cyanide over the chromate, and we know that the affinity level, or like the loveness of the silver to those compared to the chromate. This is why we use chromate as our indicator, because when the color change from yellow to red, that's the time where all that chloride got used, and silver started to form precipitate with the chromate given.
So after it turns red, even though you add more energy to it, there'll be like no change.
No change. You just start to see like a red color. That's it. You wouldn't see the increase of the precipitate at all. So in this case here, guys, we do not need to collect the precipitate and dry it, because we know we can measure the how much silver is used, and from that given titration. So this is the main difference between gravimetric and the titration analysis here. Clear? Okay. Now, what would be the limitation of this method? What could be the limitation of this method? John, what could be the limitation? This is a kind of fine, a fair method, but there is a limitation. Do you remember that I call this a high affinity? Yes. So, but there could be some silvers that are reacting with the chromate even though it has a high affinity to the chloride during the titration. Is it clear? Okay, there could be some silvers, which means that you are losing some silvers throughout the titration. So that value you got it from the titration could be a little bit slightly inaccurate. Does it make sense? And how do we overcome that inaccuracy? You titrate it with the chromate first to measure how much silver is required to change that the color of the solutions. We call that as a blank titration. So performing the blank titration means that you are getting the amount of silver required to react with the chromate first, and after you get the data from the blank titration, from the extra data you received minus that data from the blank titration, then you would get exact amount of silver that only reacted with this chloride here. Okay, so blank titration. Blank titration is known as just silver with iron with chromate only to determine the concentration of silver or amount of silver required to change the color. Okay, so the actual anode silver that's reacted is found by anode the silver from the titration, anode the silver that you used in the titration, which is total, minus that anode silver that you found in the blank titration. Copy this down on the next page. The next dot point shows describe the limitation here again too. Okay. So one issue with the Mohs method's first dot point here is the number of the silver ions in excess required to cause the formation of the precipitate can affect the titrations. To counteract this, the blank titration can be used to first determine the amount of titrant required to cause the color change to occur. Once this is determined, it can be subtracted from the volume, which means this. Okay, another issue. The Mohs method had the following issues. One, it must perform in between pH of the 6.5 to 9. Why? At the higher pH, silver ions, as we know, the silver it's a useful cation to determine the presence of the anions, but because of that, we know the silver forming the brown precipitate with hydroxide. So if the pH is too high, okay, the silver will start forming the precipitate with the hydroxide ion, which means we are losing some silver due to that precipitation between the hydroxide. That's another limitation. So you have to be careful with the pH level. Second, the Mohs method is equally sensitive to both chloride and bromide ions, which means a substance containing both ions, it can have reduced accuracy. So it's preferred that for the Mohs method, we only use to determine just one of those anions. If you have both of that, you wouldn't get the exact value. Is it clear?
So do you start the blank titration first?
We actually perform the blank titration first.
How do you perform that?
Or we just put in the silver with the chromate only, without the chloride or without those here.
So do you titrate it?
Yeah, you titrate it.
Until what?
Until color change from yellow to the red. Because what we know is the color of the chromate only is a yellow. When it has the when it forms a precipitate, the red.
And then you start putting Cl minus in.
And then you set up another experiment with the chloride or bromide or cyanide with the chromate in it.
With the chromate in it.
Mm-hmm.
But isn't it already red because you decided?
No. We set up the two separate. This is similar as a controlled experiment. Do you get it? Like
So
a
how
control.
much-
Yeah, how much is actually extra syllabus required
and
to,
then you minus
and
that.
then you minus the value, as we can see from the last value. Yeah.
So for the blank titration,
Yeah.
what will go in the
Pure.
Silver.
silver?
Is the blank titration just a titration before the actual titration?
Mm-hmm. Okay, page 68. Question 2.3 is giving you some example questions using the Morse method. Okay. No, that's actually kind of opposite method too. So, okay. Not this one, guys. Page, I have one question related to that. Question, page 72, please. Question 1, 2.4. Page 72, John. Okay, a test to determine the amount of chloride in a sample of the water was carried out. Morse method was used and a blank titration carried out with the chromate ions. It was found that 0.89 milliliter was required to cause the chromate to change the color. Now, the titration is then carried out using the 200 mils of the samples, and it found that 50 mils of the 0.45 molar silver nitrate was required to reach the end point. Calculate the chloride concentration. Now, this is the reason why I ask you to kind of memorize or understand the procedure of each of the methods, because they won't tell you sometimes, or they will describe you the methods. And this is kind of trendy HSC question styles these days. So question 1. Jeremy, what should we do?
Oh, sorry. Find the number of moles of silver nitrate.
Okay, so we're given silver nitrate here. How much is being used? 15.4 here. So we can find amount of silver ion that used during the titrations. So that would be what? Silver total that we have, which is what? 0.45. That times that 0.01550. 0.006775.
6975.
6975. Let's have a see. Okay. Wait up.
Hmm?
No. Okay. Or before we find the number of moles, first of all, so what we have to know is this, okay, guys, N total, what we have in here is actually what? N of the silver that reacted with the chloride ion plus the 2N of the silver that reacted with the chromate ion, CrO42 minus. Okay, now we can find this value here from the blank titration, isn't it? But remember the fact that we only used one type of this silver, one concentration only. So can we actually say that can be giving us silver volume in total can be found by, or amount of the silver that reacted with chloride can be found by volume in total of the silver minus volume that reacted in blank titration 2. Does it make sense to all? Again, blank titration is kind of counteracting the limitation of the Morse method, because we found that how much chromate ion is being used throughout that. So total volume that we had was 15.5 Then minus that amount of we used in the blank titration was 0.8900, so 0.8900 here. Then you should get 14.61 milliliter is the extra amount, extra volume of the silver solution that's used to react with the chloride. Does it make sense to all? Okay. Then we can now find N of silver by CV. The concentration that we have is 0.4500. That times the 14.061, so 0.01461. You should get 6.57 times 10 to the power of minus 3 mole. Okay, can we say this is actually what? Same as the chloride ions, as silver and the chloride has 1-to-1 reaction. Yep.
So kind of related to questions I was going to ask before. When we're doing like titration questions, is it best to kind of write every single equation out initially? That's what like my school teacher said.
Every single equations
Like,
related to
like,
for the chromate and everything in here.
yeah.
Yeah, if you know anything like it, it's better to show.
Do I lose marks for that, right?
You can, but for here I just kind of skipped again the blank titration because that's to show the reaction between silver and chromate, which is a kind of indicator reaction. So we're not so interested. It's not a main reaction type. We are more interested about silver and chloride, which form the precipitate. And the reason why you need to write the given any of the given formula is to determine any of the reaction ratio. So as we can get the reaction ratio from it to here, then the question asks you to find what? Find the concentration. Concentration can be found by N over V, which is what? 6.57 times 10 to the power minus 3. That divided by the volume, which is what? Given that in 200 mils, so 0.2. Therefore, you get 0.0328 mole per liter in 3 specific value. Okay, we're not done yet. We still need to find the chloride in the weight per volume. So how to find it in the weight per volume? So to convert that, the weight per volume is same as what? Gram per milliliter, isn't it? Percentage. So we have to find the grams from here. So that's same as 0.0328 times the molar mass of this, which is 35.45, divided by 1,000 milliliter. As you do so, you get 1.165 times that. So that's kind of giving you, let's do it again, 0.0328 times 35.45. You get times that 100%. You get 0.116% in weight per volume. That's the final answer.
What's so weight per volume? What's volume per volume again?
Milliliter to milliliter or liter to liter. ppm, milligrams per liter.
We have to put it percentage. We can't just leave it as like 0.00116 grams.
No, this question, weight per volume means the percentage. That's a unit of the volume too. You may get a question like finding ppm too, so especially in your test too. Just make sure you get ready for the ppm.
Grams per milliliter.
Okay. All right. That's the Moore's method, guys. So unlike the gravimetric analysis, we did not need to dry the precipitate. Instead, we could just use the constant volume of the silver that we reacted. Just get it exact from using the blank titration, and that's how you get it. Okay. One method. Moore's method. Again, you do not need to understand the name Moore, but sometimes, HSC, especially these days, just giving you some description about titrations and giving some value. You saw that one question in your topic test before, in past 2021 HSC question. Okay, those methods could be related to one of the methods we're learning, or it could be something related to something we learned before too. So you have to understand the procedure. You have to improve your skills to understand in the shorter the given time. All right, next method, page 69, please. The next method is known as Bollard's method. All right, Bollard's method uses the back titration. Highlight that, please. This is the back titration method. What that means is you may need to think about adding something in extra, in excess, and then you titrating that to get the excess amount so that you can find the amount of the reactants with reactors. So this is used in back titration with the cyanide and iron 3+ used as an indicator. All right. What we do, it's used to determine concentration of chloride, bromide, and iodide, but no cyanide in here. Cyanide was determined in the Morse method. In the Bollard's method, we can't determine the concentration of cyanide because we use thiocyanate and iron as our indicator. Again, indicator means that we only use that to get the color change so that you know when to stop your titration. Clear? Okay. So what we do first, we add excess amount of silver nitrate added to the sample being tested. So for example, you have unknown given Cl unknown chloride in here. You add some excess silver ion into it. Then what do you expect? Show me, what do you expect between like these two? There's precipitation, therefore it forming what? It forms the precipitate. Silver chloride is formed with some excess, some silver is kind of floating in the solution here. Okay? Again, Bollard's method is a back titration. So if we can get how much of silver is in excess in the given mixture here, as we know the total amount we added here, are we able to get the chloride solution? Are you able to get the amount of chloride that reacted? Okay, come back. All right, so excess silver ion is then titrated. We use that to titrate it with the cyanide. So what we do is we're using the iron 3+ and thiocyanate here again too. So you're getting that away in the conical flow with the burette. Give it over here. Inside of that, we have a SCN thiocyanide solution in there, okay, and titrating that silver chloride formed down in here, or we just titrating the for the silver in excess. As we know, the silver ion form the precipitate with the thiocyanate, aqueous, forming the silver thiocyanate. Okay, now, by just adding the thiocyanate, it doesn't really tell us when to stop because it doesn't really change the color clearly. So this is why we added some here. You add some iron 3+ into it. Just like a Morse method too. Once all the silvers get precipitated with the thiocyanate here, this is now starting to form the precipitate with the thiocyanate. Because again, silver has higher affinity with the thiocyanate than the iron. So this is once all the silvers get precipitated with the thiocyanate and moves to the next turn of the iron 3+. Yeah? Then how to find the chloride? How does it relate to chloride concentration? You all right, John? Yeah.
We can't use any cyanide because we are using cyanide.
Yeah.
That's the reason why.
Yeah. Jeremy? How can we calculate? I want to know the concentration of chloride, or I want to know the chloride number of moles. How can we find this?
Equation.
So where should we start it from?
Equation.
From here. What do we get from here? We get? Are we? How? What data do we get from this titration? Jongmin?
Amount of thiocyanate.
Amount as in what?
Volume.
Volume. You get the volume of the thiocyanate you used. You can obtain as a result. Now, do we know the concentration of that? Yes. Can we then get the N of the SCN from it by using N equals to CV? Okay. As we know that, what is this? Is this same as the amount of silver we have? Can we say that? But that silver here, isn't that some excess amount left over after form the precipitate with the chloride, isn't it? Does it make sense? This is called the back titration, guys, again. As we get the amount of excess silver in excess now, can we get the, from here, can we get the N of silver in total? Yeah, then can we get N of silver that is reacted by what? React as a precipitated. Yes, silver total from here minus the excess.
Total.
Of course you're given from here. Because you know how much you're putting in. You should design it. Here, like this. What is this? Silver. That's same as these two.
What do you need the second step?
What second step?
The second part.
Huh? Here?
Yeah, no.
I didn't get it. I showed the after effect.
From that we know there's excess of Ag.
Hmm?
Do we know there's excess of Ag plus?
Of course we do, because we designed it.
And
You get?
so that's just the result, right?
Yeah, it shows the results. You extract some, titrate it, and that. Yeah? Okay, are you sure you understand the point, John?
Where did you get the NAG total?
NAG? NA? What?
Like moles of AG plus
Oh,
total.
NAG total. You're given how much you put it into that, your design, your experiment. Okay, let's do one question. Question 2, page 73, question 2. This is showing the Volas methods. Okay, that question 2. Give you about 5 minutes to read and do this question. Okay, think about like how this flow chart, how this method is related so that you can get your value. Is that what you did in school, Jeremy? Iron and thiocyanide?
Yeah, we use like kind of.
Yep.
Was capital M the concentration?
Hmm?
Was capital M most per liter?
Capital M, yeah, most per liter. We call it a molar. This is a unit called. That's actually an old-fashioned unit.
Fajan.
What?
Fajan.
We don't use Fajans.
Was that guy? Sounds like an Indian name.
It could be a Fayan. Could be
Fajan.
yeah, could be.
Fajan.
They're great chemists in India too.
Fajan. Fajan. Fajan.
So this is the type of the flow chart you can use, or like the kind of schematic diagram you can use to understand what is going on in this question again. remember that the back titration is the finding the process of finding how much of the in excess. And direct titration is something that we directly find how much moles is being used. There could be a chance you get a back titration question in your coming test. So, from the topic test questions that I gave you, there's a one back titration questions. Make sure you try that before you go. Okay. Finished, John? Still getting? Okay, finished? Getting there? 2. Question, student wants to calculate the concentration of the iodine in a commercial brand of the antiseptic. 10 mils of the antiseptic was reacted with 25 mils of the 1.05 molar silver nitrate. The excess silver nitrate was titrated with the 0.4505 molar sodium thiocyanate, which also contained iron 3 ions. The end point was reached when 32.45 mils of sodium thiocyanate was used. Calculate the concentration of the iodine in the original sample. So you have to understand that as iron in the given sample as you worked as an indicator, because what we know at the end of the all the silver, excess silver got titrated by the thiocyanate put it in. Ions are started to get forming the precipitate with this complex precipitate, turns the color change to the red. Okay, now this is really helpful if you understood the Volar's method prior to this question. Okay, I'm giving you some advantage so you know what is going on, and then you can start your calculation quite easily. So what we have to do first, we can find silver in total, which is same as N of the silver nitrate. That's found by CV. This can be found by what? 1.05 times that, 0.025. Then what you should get 0.02625 mole. That's the total amount we put it into the silver here. Yes, this is what I said. You're given. You will be given how much you put it in here. Okay, then what we know. We need to find that, as we know, the silver, I use this space, silver forming the precipitate. This is what you need to show in your answer to. You need to show the chemical form equations if you know there's any reaction involved, which form the silver thiocyanate solid is formed to. Okay, then N of the excess silver. And the silver in excess can be calculated by the C of the NaCN times that volume, that how much is used. Because the reaction ratio between silver ion to thiocyanate is 1:1. Makes sense to all? So what we have given is 32.45. The concentration of the thiocyanate was 0.4505. That times that 32.0.03245 here again too. Then you should get the value of the 0.01461 mole. Good? Now, finally, we can find the silver that's reacted or formed the precipitate by how? This can be found by N of the silver total minus that N of the silver in excess. We found them all. Total is known as 0.02625 minus excess 0.01461. We got it up to here? Okay. Did you guys get the 0. What? 0.11 mole? Good. Are we done? No. You need to show another formula that the silver reacted with the iodide forming what? Silver iodide solid precipitate. Okay, here I use this chloride because as you're given iodide here, the N of the iodide, can we say that's the same as what then? Therefore, the same as silver. That's a reactant, which is the same as 0.01163 mole here again too. Are we done? Yes, we need to find the concentration. By what? N equals C equals to N over V, 0.01163. Show me. Volume. What's the volume? You should get 1.16 mole per liter in given three specific values too. From 4 and 3, choose 3. Okay, back titration again. High chance you get the back titration question in your trials. This year's HSC, there's a chance you can also get the back titration process.
When did you get a new laptop?
When did I get it? Last year.
This is a new model.
Last year, yeah. It was new model. It was new, not now. There's a new model coming out soon. Every year.
Every year, yeah.
Every year. This
It's so sad.
is an M1 Max or something.
It's M2.
Yeah, now it's M2 Max, yeah.
It's so clean.
Yeah,
The charge is nice as well.
exactly,
It's
yeah.
not a Type C charger though.
Neither.
That one should be Type C. Isn't it?
There's a Type C and the magnetic too.
Oh, does it have both?
Hmm. MagSafe.
So cool.
Do that again.
Yeah. Get it?
Hakuna Matata.
Hakuna Matata. Seize the day. All right, limitation of Bolas method. Highlight this, guys, too. The limitation first. When the precipitate being tested is more, sometimes, AgC, for example, is more soluble than silver thiocyanate precipitate. That's great. Oh, okay, so this will cause the end point to be reached sooner, giving higher concentrated silver ion in excess, which leads to the lower concentration. So because silver chloride or the precipitate we have, for example, silver chloride is more soluble, yes, it could be one issue. So to overcome that, we can filtrate all that precipitate we have, or by adding few drops of the nitrobenzenes to precipitate to stop. The iron 3 ions could also be hydrolyzed in alkali condition to form iron 3 hydroxide, so that to overcome we have to perform the reaction in the slightly acidic conditions too. You may or may not need to know this, but okay, these type of limitations, guys, I'll show you one question in a minute, last year's HSC question, something you should think of before you doing some questions in HSC. All right, last one, the Fajan's method or Fajan's method. We do not really use lots of Fajan's method, to be honest. This is something not really part of the HSC syllabus. I just put that because there's one school, I forgot which school was, 2 years ago. They actually had giving the depth study for this titration method. Okay, this is something we use the least. We don't really perform because due to that, Fajan's method uses a very specific indicator. The fluorescein or the acene is something we use. The fluorescein must be in the pH of the 7 and 10, and the color change from yellow green to the pink. Acene is used for the halides except the chloride, and acidic conditions it will change the pink to red violet. So this is the direct titration. Okay, reason we don't use that is it's not so accurate, and sometimes it's hard to get these indicator in the school laboratory. So this is something that we don't really do a lot in New South Wales. They may do in Victoria maybe.
Really?
What Victoria?
The VCE system is quite different to the HSC, so yeah, maybe. I don't know. I'm not an expert at the
Is it
VCE.
better?
Similar.
Skinny.
Similar.
It's like a skinny.
Okay.
We do VC questions in maths.
All right, page 74.
Victorian HSC. Remember that walking process?
Okay, we're gonna start from page 74 next week. Okay, from here. And I will actually give you some